Good morning. Hope you guys enjoyed that nice foot of snow we had in Colorado. I'm sure it's going to melt in the next 3 days, and we'll have 65 next week. Today's agenda, we are going to graph what are known as parametric equations. Much like a lot of the topics that have been in college trigonometry, it is probably something you've never come across before, unless you just happen to have used them but not derived them in an upper division science class. We're also going to be able to find the connection between a rectangular equation for a curve that has been defined parametrically. You should be very comfortable with the rectangular system. It has been the primary system that you have been using in mathematics for the majority of your mathematical life. If you look on Google Classroom, there is a problem set /20, so make sure you get a chance to take a look at that and check all your solutions before you submit it. Here we go. A function. It is that word you have heard over and over again. Most of you were repeating the word function when you were in junior high, but not really understanding what it was. By definition, a function is a mathematical relation in which every value in the domain has just one corresponding value in the range. You guys were taught that a function will pass what is known as a vertical line test, simply showing that for every point P, wherever it is on this function, and I remind you, not every function is continuous. You have learned about many types of functions in your library of functions. You'll investigate more, even so, in calculus, and if those of you continue on into the applied mathematics field, you'll see how we can use mathematics. Every value in the domain, in this case, the x values, will only for you determine one particular y value. Functions are a specific type of mathematical relation, but not all relations are functions. Just like a square is a type of a rectangle, but not all rectangles are squares. So this, which is called a plane curve, it is not a function. Why is it not a function? Well, that's because, as you can see, some values of x, in this case, this one right here, gives you two particular y values that happen to be different. One value of x has not defined a singular value of y. So what do I know? I'm going to step back from this. Not worry so much about what a function is, but recognize that these are both called plane curves. And they are both relations, which are simply collections of points in the xy plane. So we've focused most of our time on functions, and now we're looking at all plane curves. So here we go. What if, and that is the beauty of mathematics. Some mathematician thought about that wonderful phrase, what if? What if, for a plane curve, we were to look at x and y not as a pair, but rather values that are derived independent of each other? Meaning every x value is actually coming out of a function I'll call f. And every y value is actually the end result of a function I'll call g. So g and f are actually defining x and y at this point in time. Now, both g and f are going to be based on some other particular domain value, which I'll call t. And obviously, in most cases, t is referencing time. It is time that is used in so much applied mathematics. So one more time. What is x? What is y? Well, if I go back to this right here, x and y simply correspond to the horizontal and vertical movement of a particular point. And as you can see, as I trace point P, every point P, its horizontal and vertical components are changing. Now, the location of point P is at that snapshot in time, its exact horizontal and its exact vertical distance. But when I think about it in this terms, I can maybe define those horizontal and vertical distance as functions themselves of a particular variable, in this case, t. Some vocabulary for you. Number one, f and g are two functions who have a common domain. and that domain is in some particular interval that I'll call I. Second of all, t, which is the independent variable going into the functions g and f, which will help me to determine x and y, all these values of t exist in this common interval where f and g are both defined. Okay. X and y are called the parametric equations. They are two individual equations that help define for me a particular plane curve. They're called the parametric equations at that point in time. T itself, which is going into the two parametric equations, is called the parameter. Just some vocabulary for you to become comfortable with. So what does it look like for us? Well, here we go. This is an example of some parametric equations. It looks like we have x is defined to be by 3t squared and y is defined to be 2t. Now, of course, you guys recognize x is being defined by a quadratic function and y is being defined by a linear function. And we are going to set the interval that t exists in. T will be greater than or equal to -2 and less than or equal to 2. And we're going to wonder about the plane curve that is defined by these two. So let's go back to how we used to do it way back in the day. Every individual function you ever should have developed should have been done by a t-table. So let us pick some values of t that exist within the allowable interval. And I have chosen integers just because it makes life easy. All I would do is I would plug in the value of t respectively into the x. You can check my calculations. Hope I haven't made a mistake. Let's choose one randomly. T is 1. 1 squared is 1 times 3 is 3. So when t is 1, x is 3. I would then plug those t values into this parametric equation, which helps define y. And there we go. Let's just check one to be sure. -2. -2 times 2 is -4. And the plane curve is then defined by each particular parametric equation that are then put into a particular point of that plane curve. So there's a t-table like we used to do it, but now we're using what are called parametric equations. So if I was to plot all those points, I would end up with something that looks like this. You guys, of course, would recognize that as a horizontally opening parabola. It is a plane curve, but it's definitely not a function. For example, at an x value of 5, 5 defines two different y values, not a singular y value. So I think we spent a lot of time in our section on conics on how to define this in a rectangular form. I just want to show you that I can also define it using parametric equations. What is the rectangular equation with this? Well, I came across a process of developing that back in the conics, but now maybe there's an easier way of going from parametric equations to a rectangular equations. And that is what we've done time and time again all the way through college algebra, is think about the process of substitution. I notice both x and y are defined by t, so maybe I'll just do some simple mathematics. Notice in this case, that means that t itself is y over 2. Well, this t is consistent with that t, so I think I'm going to use substitution. So x now will be 3 times the quantity of y over 2. I've substituted that in for t squared. I'm just going to let math take its course, and I end up with the beautifully done equation in rectangular form of this particular horizontal parabola whose vertex is at 0, 0. And from there, of course, I could find the endpoints of the latus rectum. I could find the focus, values of a and b and c. Are they all so simple? Well, it's the same process every single time. It's just perhaps some of the algebra changes. So let's take a look at something that might throw you for a loop briefly. Briefly is the key thing. Let us find rectangular equations for the following curves defined by these two parametric equations. X will be defined by -a times the sine of t, and y will be equal to -a times the cosine of t. T will be defined in the interval from 0 to pi, inclusive, so I'm talking about quadrants 1 and 2, and the A values themselves will always be positive. Okay, if I just stick to what I did on the previous slide, the first thing I'm going to do is solve for something. So I've decided to solve for the sine of t and the cosine of t by simply dividing both sides of the equation by negative a. And that has led me to that. Now, why am I doing that? Well, that is trigonometry at its finest. Whenever I think about sine and cosine, I think about these established relationships that we have developed over the course of the year. And one that comes to mind right now for me is definitely the Pythagorean identity. I know what is always true, that the sine squared of t plus the cosine squared of t is equal to 1. Why do I look at this one? Because I've solved for both the sine of t and the cosine of t. So now I think I'll just use substitution. So I've plugged in what I now know the sine of t to be, the cosine of t to be, and I'm going to square them according to the Pythagorean identity. Notice I am going from trigonometric functions to a particular equation that does not have them anymore. The beauty of substitution. So taking into account squaring things appropriately, that leads me to this. Noticing that this is a plus sign, these are the exact same denominator. How about I just head to this? And I should recognize this. This is simply the equation of a circle. No doubt about that. And this circle is centered at 0, 0, and its radius apparently is a. Well, what does that look like in terms of the parametric equations? Well, it says that t can only be defined in quadrants 1 and 2 from 0 to pi. So I think what I'm going to do is I'm going to choose a value of 0. Makes sense. Choose a value of pi over 2. Makes sense. And choose a value of pi. Makes sense. And this right here says that I can choose all three of these values. And those are, of course, quadrantal angles. When I take all three of those angles and I plug them in to find the x, says right here, the sine of 0 is 0. 0 times negative a is 0. The sine of pi over 2 is 1. 1 times negative a is negative a. And the sine of pi is 0. And negative a times 0 is 0. And I can multiply negative a times 0 because I've defined a to be a value greater than 0. Therefore, the opposite of that would be value less than 0, which times all our values, it doesn't matter. It leads to the same thing. Y, plug in your particular three angles for the parametric equation for y. That leads to this, and to that, and to that. Now remember, these now correspond to the points on the plane curve. And if I was to graph those, I would get something like this. Now notice that since I have defined the interval, this particular plane curve, you're quick to say, oh, it is a function. No, of course it's not a function. There's clearly every x in this case has two, there's some x values that have two corresponding y values. But nonetheless, that's how I can use trigonometry. That's how I can use rectangular equations, and I can understand how parametric equations could be helpful in the future, which we'll take a look at in a future class. Have a great day.